One of the most common and important chemistry procedures done in real chemistry labs is called titration. In titration, you're taking one solution whose concentration is known and using that by reacting it with another solution to find the concentration of the other solution. But to actually find the concentration, you have to do some titration stoichiometry. Yeah, I know, stoichiometry is rearing its ugly head again. So titration can be generally defined as taking one solution whose concentration is known and using that to find the concentration of another solution for which the concentration is not known. Okay, so you're taking one solution with a known concentration, using that to find the concentration of another solution. Now, titration is used for a lot of different things. It's used a lot with acid-base chemistry, and that's what we're going to use it for here. All right, so if we start by interpreting this problem, we want to find some important things out about this. First of all, I'm going from one chemical species to another. And so if I'm going from one chemical species to another, I must be doing stoichiometry. All right? It's titration because I'm using molar concentration of one species, this sodium hydroxide here, to find the molar concentration or molarity of another species. Okay? So we're going to have a molar ratio, and a molar ratio comes from a balanced chemical equation. So stoichiometry requires a molar ratio. Molar ratios require a balanced equation. We need to figure out a couple things as far as terminology here. What is the chemical species we are analyzing here? Sodium hydroxide? Well, we know its concentration. We don't know the concentration of, we're trying to find the concentration of acetic acid. So that's what we're analyzing. Okay, we're analyzing this because we don't know its concentration. And so this species is called the analyte. Okay? Now this process of putting an amount of solution whose concentration we know into a solution whose concentration we don't know to find the concentration of the other species, that's called titration. Okay? And so the thing that we're using to find the concentration of another solution, this is the titrant. Okay? For acid-base titration, neutralization occurs at an equivalence point. Now, you should know enough now about acetic acid to know it's a weak acid. Okay? And it's monoprotic. So monoprotic weak acids, when you titrate those and look at the titration curve that results, the pH never gets down to 0 down here. So we're starting somewhere along here. We get that long sort of plateau area, or sort of a shallow hill, or not a very steep hill here, before you get to that steep cliff face where the equivalence point is located. So there's an equivalence point in here. All right? The equivalence point occurs is when you add enough base solution. Well, that's what we're doing. The independent variable here is adding the base solution to that point where we reach that equivalency. The equivalency occurs when we have an equal number of hydrogens for that dissociation of hydrogens. There's only one for this acid. An equal number of hydrogen ions and hydroxide ions from the base. Hydroxide ions come from the base. Hydrogen ions come from the acid. Okay? So we're analyzing this problem, trying to figure out what are we looking for and what are we trying to get to. Okay? And those are some of the things you need to know. The analyte is the thing you're analyzing. It's the solution whose concentration you don't know. The titrant is what you're using to find the other concentration with. That's the titrant. It's titration because we're putting one solution into another to find a concentration. That's what titration is all about. Okay? You with me so far? All right, let's try to solve this problem then. First thing we've got to have is a balanced equation. And you should know how to figure out what the formula for acetic acid is. And a name for an acid like this IC ending, could stand for a binary acid, or it can also stand for an acid that has oxygen in the anion part of the formula if the anion has an AT ending. Since if it was a binary acid, there'd be a hydro on the front. There's no hydro on the front, so this is an oxy acid, one that has oxygen in the anion formula, and the ending of the anion, it has an 8 ending. So this is acetate. We're looking for the acetate ion. The acetate ion is CH3CO2 negative. Okay? And so to find the acid of that, we're just going to put as many hydrogen ions on there as we need to neutralize it. And one hydrogen ion with a plus sign is going to neutralize or wipe out the charge if I have a 1 negative charge on this anion. So the formula we need for the acid is HCH3CO2. Now that's writing the acid if it's a non-organic acid. In fact, acetic acid is an organic acid. We could also write the formula for acetic acid with the hydrogen on the back, because in the structure of an organic acid, the H actually attaches to one of the oxygens here on this CO2 group. Okay? So if I were writing this as an organic acid, I'd write it that way, and you would have to know, you should know, this is the hydrogen that dissociates. If I write it like this, which is like representing it as if it's not an organic acid, then the hydrogen that's coming off is the one on the front. These 3 hydrogens here, they're attached to carbons. Those hydrogens there are not ionizable. Okay? They're not dissociable. All right? Only this hydrogen, which is attached to that oxygen on one of these 2 oxygens here on this CO2 group, only that hydrogen is actually the one that can come off. So this is a monoprotic acid, not a tetraprotic acid. Okay? There's not 4 hydrogens that can be removed, only 1. So this is going to be dissolved in water. It is a solution, it says so up here. And we're going to react that with sodium hydroxide, which is in solution. And so it's going to be dissolved, we'll call it aqueous. And 1 hydrogen and 1 hydroxide, we're going to form 1 water molecule for every one of these and one of these. And then this part joins up with the back part of this. This is a double replacement reaction. All of the acid-base reactions we worked with in this class are acid-base, except for some single replacement reactions we dealt with, but we don't often call it acid-base for that. Everything we do in this class we called, if it was an acid-base reaction, it was also double replacement. So sodium then joins up with the acetate. Now it's also acceptable, if you want to write this reaction like this. Now you can't write water as a separate hydrogen ion and a separate hydroxide ion because those actually join up and make a molecule. So those are not ionized anymore. But this sodium really is dissolved in water, so it actually remains in solution, as does the acetate ion when you're done. So you can write these out separately if that's what you prefer to do. Doesn't really matter. Okay? All right. In any case, we need to balance the equation, and we use an atom inventory for that. So we've got H's, hydrogens and carbons, and oxygens and sodiums here. And I see 1 plus 3, that's 4, plus 1, that's 5 hydrogens. I see 1, 2 carbons. I see 2 oxygens here and 1 there, that's 3. And I see 1 sodium. And that's all on the left-hand side of the equation. On the right-hand side of the equation, I see 1, 2 hydrogens here and 3 here, that's 5. I see 2 carbons, 1, 2, 3 oxygens, and 1 sodium. So the equation is balanced. We're ready to start the stoichiometry. So we're going to start with the volume of the solution whose concentration we know. Okay, that's one way to think about it. You start with the volume of the solution whose concentration you know. Another way to think about it is you always start with the amount of titrant. When you're doing the titration stoichiometry, you always start with the volume of the titrant in the stoichiometry. Now, you could do it another way, and it'd come out just fine. I just suggest you start it that way because it kind of works out easier that way, all right? So we've got this amount of this stuff, this sodium hydroxide solution. Okay, and it doesn't say sodium hydroxide solution in this problem, but if there's a molar concentration of it, it must be a solution because that's what that applies to. Molar concentration only applies to solutions. So we're going to start with this amount, 25.19 milliliters of that sodium hydroxide solution. And we're going to put that over 1, just like most of the other stoichiometry problems we've done in the past. Oop, I meant that I cover up just the top half of that. There's a decimal place there somewhere. All right. We're going to use the molar concentration now to get the moles. But remember, molar concentration comes in moles per liter. So I can't use milliliters. I've got to change this to liters. Okay. What I'm going to do then is to use this equality statement here. This is a defined equality. 1,000 milliliters equals a liter. I want to put 1,000 milliliters on the bottom and 1 liter on the top. And I can change now the volume into liters. Now we're ready to use the concentration to change this into moles. Okay? And I want to put a time sign here. And we know that molar concentration is moles of this species, sodium hydroxide, over 1 liter of that sodium hydroxide solution. Okay? All right, canceling as we go. Now we can cancel out sodium hydroxide solution and liters, and we're at moles. Once we're at moles, we can convert to moles of the other species, the one we're looking for, using what's in the balanced equation. I want to match the units and species that are on the top of this fraction with what I put on the bottom here. So I want moles of sodium hydroxide down here, and I want moles of what I'm looking for on the top. Well, the problem says what we're looking for is the concentration of acetic acid, and that's this chemical species here. So on the top here, I want moles of acetic acid. And in this equation, there's a 1-to-1 ratio. So we've got 1 mole of sodium hydroxide and 1 mole of acetic acid. Okay? I can now cancel moles and sodium hydroxide. All right, now we want to get this into molar concentration because we're looking for molarity. That means we want moles over liters. The problem doesn't give me liters, but it gives me milliliters, which we already know I can convert to liters. So I'm going to put this on the bottom because that's what I want this to come out to be. So 1 over 34.57 milliliters of this acetic acid solution. Okay. And I'm going to have to convert using this equality statement here we started with over here. I want milliliters on the top this time, 1,000 milliliters over 1 liter. All right. So now we've got milliliters that are canceled by milliliters. And I have arranged this problem so that I've got moles of acetic acid over liters of acetic acid solution, and that is what molarity of acetic acid should be. So we're ready to do the math. Your calculator might not give you as many digits, but that's okay. You write down the number of digits you have on your calculator. What we have left are moles of acetic acid over liters of acetic acid solution. We need to round our number off so that it matches the correct number of significant digits. We're going to look at the problem and see of the measured numbers and calculated numbers we have that we have 4 significant digits. This one has 4, this one has 4, and this one has 4, so we want our final answer to also have 4 digits. Leading zeros are not significant. 1, 2, 3, 4 digits. Round off from here. 0.07469. That 8 makes this 8 round up to a 9. And moles of acetic acid over liters of acetic acid solution is the same thing as molar concentration of acetic acid solution. And this is the answer we're seeking here in this problem. Well, what I did was I noticed that I've got milliliters, and I can't cancel out liters of this with milliliters. But that's a really good point that you noticed here, okay? The question is, why do we have this over this and we just turn around and put reverse it over here, okay? Because if you're doing it step by step, you need to do this. However, if you can see far enough ahead, and I say this with a great deal of trepidation because I'm scared that some of you are going to see this and say, I can do that, and on the test they're going to mess it up, okay? So if you're not absolutely sure that you can see that I'm going to be doing this and then this, and you don't need both of them because one just undoes the other, then put them in there. But if you can use it and do it correctly and don't put that in there, basically you can cancel this milliliters with that milliliters over here, okay? This one can be canceled with that one, and you don't even need these 2 steps right here. Now, if you have an acid with more than one ionizable hydrogen, which is to say you've got a diprotic or triprotic acid or some kind of polyprotic acid, then you've got to write separate dissociation equations for every hydrogen ion that's going to be removed. Titration of an acid, we only worry about the first hydrogen that's being removed, at least typically. So we'll write an equation that looks something like this, where I've written our general formula for an acid, HA, with H2A to show that I have a diprotic acid, 2 separate hydrogen ions that can be removed. When we remove that hydrogen ion from the acid, the product we're going to get will be HA negative, pull off positive hydrogen ion, and what remains is an HA negative. The BOH represents our base, where we have a metal ion with a positive charge attached to the hydroxide that forms the base that we want for our titration. Now you can write the equation in 2 different ways. You can write it in the first way I'm showing here, where we write the ions separately, where B plus, representing our metal ion, is written separately from the HA negative, or as we did in the second equation, where we've combined those 2 into a salt. There's no hydro prefix, so this is probably going to be an oxyacid. An oxyacid is an acid that has a polyatomic ion that contains oxygen. Ic comes from the 8 suffix, okay? And phosphate is PO4, 3 negative, so phosphoric acid is H3PO4. So there are 3 ionizable hydrogens we would expect, and this is not a strong acid. The way you figure out whether it's strong or not is you have to have 2 or more oxygens than hydrogens. There's only 1 more oxygen here. So this is a weak acid. So we would expect our curve to start somewhere above 1. You're going to have a long plateau or a hillside. You're going to have 1 cliff face, 2 cliff faces, and if it can be seen, a 3rd cliff face. Okay, that's what our expectation is. And we're looking for the equivalence point right here, which is the removal of the first hydrogen. The removal of the first hydrogen then gives us H plus and H2PO4 negative. Okay? So the equation then will look like this. Okay? Phosphoric acid, potassium hydroxide, water, and here's the H2PO4 with the potassium on the front, or alternatively, a potassium ion and an H2PO4 ion. This gives us a 1-to-1 ratio between the acid and the base. So our molar ratio is always going to be 1-to-1 for stoichiometric calculations in titration. Okay? So we're starting with we're starting with the chemical species whose volume and concentration we know. So we know the volume of KOH and we know the concentration of KOH. We're going to use the concentration to change this into moles. We get moles here, convert to moles of the acid, divide by the volume. In this case, I've set it up so I can cancel milliliters with milliliters and leave myself with liters of the acid solution. I come up with this molarity.